Thank you, Glenn.
Thank you.
Good afternoon, everyone.
Yeah, I can hear you fine.
Yes, perfect. So good afternoon, everyone. Welcome to this presentation on the multiphysics optimization application of surrogate thermal models. It's a lot of words to say, so what do we want to talk about, really? Basically, we're going to start out by looking at some of the challenges that still exist when you run analysis today, so in 2020. We'll look at a real-world example that we ran through, and then go through how you can set up design space exploration models, you set up surrogates, and particular emphasis on how you create the interaction between TFAWS, which is a design space exploration software, and SimCenter 3D. We'll also talk a little bit about sampling the design space and then generating and evaluating a surrogate model. So we'll go through what all of this means and why we're doing all this. The next step, we'll look at the multidisciplinary analysis and how we go about doing that, and then we'll conclude at the end with everything that we covered and why we go through all of this in the first place. So as you know, model analysis are multidisciplinary, which means you need to optimize parameters across different disciplines, and they all need to be optimized at the same time. You can't, they all have competing requirements, right? Whereas, a structural designer wants something to be stiffer or stronger, but they at the same time they want to keep the mass low. The thermal analyst wants things to survive the harsh thermal environment out in space there, but may not be able to do so with the competing effects of the other disciplines. So it's basically this interaction and collaboration between the different design teams is necessary in order to have a successful design and mission going forward. One of the other challenges you have is that size of the models are increasing. It's not just mesh size, but also in terms of the complexity of the device that's being created. So as this gets larger and more complex, it becomes harder and harder to simulate this in its full glory, as one would say. But the challenge there is then to handle design space exploration faster. How do you go about doing that? How do you get things to run faster? How do you get answers faster? So these are the questions we'll go through. And of course, all of these different analyses are handled with different software. In an ideal world, they'll all be in the same package, and they'll just kind of switch environments, or even not even switch environments, just change PCs, but that's not how it works today. What we do need, though, is to have these pieces of software work together in a way to have them interact with each other. Essentially, we want to pass data back and forth between them. So these are little charts to just give a quick overview of what we're talking about. You've got the mission design, and then you've got, someone comes along and does the CAD design, and we do thermal analysis, and then we look at thermal elastic distortion, go into optical analysis, and then there's also the structure modes and vibration, power budget analysis, link budget analysis, and all kind of linked together in some form. So what we really need is a way to have a workflow orchestration software and a multidisciplinary design optimization software. So we need to somehow be able to not just create the workflow, but also track it from start to finish. So here, Maya, what we did was we took an example of a microsatellite, and the goal was to demonstrate the use of a miniature infrared sensor, right? So what we did was we took an MDO software, in this case it was SimCenter TFAWS, to do the design space exploration, the surrogate modeling, and the multidisciplinary optimization of this model. The CAD thermal and structural models shown here, they were all developed within NX and within the SimCenter 3D environment. So they're all happening on the same platform, as it were. The CAD doesn't need to be translated into different solvers. All we need to do is just create the relevant, finite element models or the relevant meshing for each of the different solvers. Depending on how you approach it, sometimes you'll need to do one mesh. But in this case, we have to do two, and we'll get to why a little later. The thermal model that was developed, that took about 8 minutes to run on 6 cores. So it's fairly quick by today's standards, but you can imagine on a larger model that 8 minutes can easily go up to 8 hours. So that's what we want to show how we can reduce the time to getting the answers that you're looking for. The thermal design basically involves exploring the effect of different design parameters. Typical ones in this can involve, the emissivity, absorptivity, but in this case, we were looking at the radiator dimension and the radiator optical properties. And then the thermal and structural analysis must be performed, and they have the typical objectives of, minimizing power requirements, minimizing the weight. Nothing new there, but it's just to use as an example. And then there's obviously going to be constraints on the performance as well. So you need to meet the temperature limits on the components, and you have to make sure that the IR sensor meets the targeting requirements, which means you have to limit misalignment, and misalignment comes from the thermomechanical deformation that occurs due to temperature gradients in the device. So several simulation cases, they were all run in SimCenter 3D Space System Thermal. We had the cold case with standby power, the hot case with operational power, and the orbit itself was essentially a sun-synchronous orbit, and it was simulated to a periodic steady state. We'll get to that second point a little later as well, and why that's useful. The design parameters, we were basically looking at the radiator emissivity, absorptivity, and then varying the height of this block here automatically, right? So how does this set up? So once you've got your thermal simulation set up and it's running, and you've got one set of results, you can fire up the design exploration software, in this case HEAVS, and just load it up into the HEAVS environment. So there's a portal that gives us a native connection to SimCenter 3D. And once you load up that solution, or rather the simulation file, it'll actually read in all the solutions that you have there, all the variables and the results, and you can start defining what your design space exploration should look like. So once you've got your solution set up, you can say, okay, well, I want to look at, for example, this second solution here, and then I'll tag my variables. In this case, what we mentioned earlier, the height and the thermal optical properties. And then you've got a set of responses that were obtained also from the results. So these are all coming from the model itself, and you can keep track of how things are changing as the variables change. Next thing you do is you specify design of experiment parameters. So you've got your variables here, you've got your low and high values, and then a baseline value. And then you instruct the software to do a sampling on these variables, right, based on the number and so on. So you have to specify the sampling method. In this case, we chose Latin hypercube, and then you basically ask it to go explore design space. And what you see at the bottom here is an animation of it going through the different scenarios, computing the temperatures, and then we get the response plotted based on the change in the variables. So a question that comes up usually is like, well, what kind of sampling method you would use? I mean, that depends on what your intent is, but essentially, rule of thumb, you want to have enough samples to capture the response surface well, but not so many that you take a really long time to run the simulations. Right? So that's what you would do. So eventually what you'll end up with is a response surface that, looks something like this. In this case, it was fitted with a radial base function surface, and it was the response surface for the battery temperature. So when you're going deeper into this design space exploration, 8 minutes, running a single model is one thing, but then when you really want to explore design space, it can add up really, really quickly. So what we do is we do a set of design, the sampling that we showed a slide earlier, and then create a response surface. And then that response surface can be used as a surrogate thermal model. And that surrogate thermal model can then be used for further analysis in MATLAB and Python. So now you're going into system level analysis for including the responses of the battery in this case into your system. So you don't have to rerun the the 3D model over and over again. You just need to have enough data to feed the surrogate model, which is then used in the larger model, and therefore get it to go more quickly. So the next steps with this particular effort is to do a designer experiment with the hot and cold cases and actually do an optimization of the radiator size. And then the idea being to minimize the heater consumption and then respect unit temperature limits. So again, it's the same idea. You would take the response surfaces rather than the full 3D model and then run through the design space exploration with the same tool. So it's all happening with the same environment, same tool. We're just changing what we do with it, essentially. So after this step comes, once you've done all your design space exploration, you've come up with a bunch of designs that you really want to dig deeper into. Then comes the step of doing multidisciplinary analysis, right? So within the SimCenter ecosystem, there's a couple of ways you can do multidisciplinary analysis. One way, in this case, we're focusing on the thermal structural analyses, but one way to do that is to have a one-way mapping between SimCenter 3D thermal, so you take the temperatures, map them onto a structural model, and then run that structural model in SimCenter Astron or SimCenter durability, depending on what you're aiming for. So essentially, you would run the entire model, and then you'd map the temperatures over. There's also the ability to do a two-way, fully coupled, nonlinear thermal structural analysis, including contacts. So what we have here is an animation that shows in a gas turbine engine, you've got the blades and the entire axisymmetric model line is kind of deforming, and then one of the blades is impacting the shroud, which you really don't want. But this is also a possibility. For the purposes of this presentation, though, we'll look at the first method, which is mapping temperatures onto a structural model. And part of the reason is that the thermal mesh requirements are very different from the structural mesh requirements when it comes to working on things like spacecraft. The thermal mesh needs to be needs to take into account the fact that you need to do radiation calculations, so you have to be well aware of the view factors, and the structural model, of course, has to have very nice meshes, irregular meshes, and so on. So what we need to connect these two is to have a very nice mapping process. So this is something that we do have, and it supports mapping between the similar meshes. So you can see these two meshes are not very alike. They have different mesh types and different mesh sizes. And also, because of the implementation of the algorithms, we support mapping between congruent geometries. So they don't have to be identical. I mean, if you look a little closely at these two examples, you have some different features that appear on one but not on the other. But that's okay, because the mapping takes care of putting the temperatures in the right place on the structural model. So overall, the process looks something like this. You would do a thermal simulation of the entire spacecraft in orbit, but what you're really interested in is what's happening to this IR sensor module, right? So, but you do need to have all the shadowing and everything taken into account when you do the thermal simulation. Then you take those temperatures and map it onto the structural model, and then you do the structural analysis of the sensor. During the mapping process, you need to have, we have the ability to do very fine control of what maps to what. It's not necessary, but it really helps. And then, of course, when you have a structural model and you've got all these, different temperatures at different time points, you have to create all these subcases. If you were to do this manually, it would be quite tedious. So what we actually do is to create all of this automatically with basically create a structural solution with the suitable subcases, and then all you have to do is put in the rest of the VCs and you're good to go. All right, so let's start with the first one. We talked about it a little bit, so we're just going to skip to the results, which is always nice. Basically, you'd run the same kind of orbit that we talked about earlier, verify that the results make sense. So here we're looking at this in the orbit visualizer in SimCenter, and you can see the temperatures vary as it goes around the Earth there. The other thing we want to verify is that the shadowing is being correctly accounted for. So here we just look at just that IR sensor, and we look at the absorbed influx from the solar radiation. You can see that while it's behind the Earth, of course, there's no solar radiation absorbed, but as it starts to face it, then you can see areas where you may have increases in temperature. because of the incoming solar flux. The solution is run up to a maximum of 10 orbits, but we actually have the ability to detect periodic convergence. So this takes out a lot of the guesswork out of when do you stop a solution? How do you know that you reached some sort of periodic steady state? The solver does that. And so we just set it to some large enough number of orbits, and then we allow the solver to figure out where it's reached a periodic steady state. And then we focus our analysis on the last orbit, because that's where we know, okay, that's the cycling of the temperatures and everything that we're going to be seeing while this thing is in operation. So the next step is to then take the temperatures and map it onto the structural model. So the first thing is, we did the whole spacecraft, but really we just want these temperatures, right, on the IR sensor, and that's possible. I mean, we have these what we call simulation objects, but really what they tell the software is that, okay, we want to map this zone to this other zone, and so on and so forth. And it doesn't matter whether the models are aligned or not. So, in the spacecraft, the IR sensor is modeled something like this, and then in the structural model, it's got a completely different coordinate system. That's okay, because all we need to do is to say, on the thermal model, okay, this is the area of the lens, and it's going to be mapped onto this area of that's the lens on the structural model. So these mapping constraints, as they're called, they enable accurate mapping even when the geometry is not aligned. So you'll get this much more control over what to map, where to map it, how to map it, and so on. Again, this is not necessary. I mean, it's solver's quite smart. If you give it enough information, it will do the rest of it automatically. But in this case, we wanted that kind of control, and we did it, set it up that way for this example. And then after that, we do the structural analysis, right? So we put in all the rest of the DCs, and off it goes. And here's a picture of the results, inside the IR sensor. And we see some deformation on, well, this plane is actually an electronics board. But what we're more concerned about is actually the misalignment of the IR sensor and the surrounding structure. So right here is where the detector is. We don't want this to be misaligned. We actually checked the lens. The lens was okay. We turned out that this portion was problematic. So here's a few cases where we ran hot and cold cases, and then BOL, EOL for multiple properties. And in general, what we saw was there's an order of a tenth of a millimeter deformation on that detector, and that's for something that is highly sensitive. That's not so good. So we want to reduce that if we can. And it turned out that it was really just a matter of adding a few more restraints on the structure itself. So you rerun the case, you add those extra fixing points, and what we managed to do was reduce the deformation of the detector by an order of magnitude. So that's a big deal. That's a big win. That means that we've actually solved one major problem before it actually happened. And what we did throughout was actually run through essentially a workflow, right? So we did a thermal analysis, we then mapped them, and then ran a structural analysis, and all of that was done by within the same environment. This entire process, even though it was done partially manually, as in you would set one up, and then hand off data within the software, this can be automated for design space exploration. And we will talk about this in a subsequent paper, but all of this can be done automatically, and you can specify all your variables and do a multidisciplinary optimization and make sure that you find the right design for your mission. So to conclude, basically we showed two methods or two capabilities that come in really, really handy. One is when you're doing design space exploration on a thermal model, you want to get this model to run faster, or design exploration to run faster, and so what you would create is a surrogate model, which would then be used in other analyses. And then when it comes to doing multi-physics or multidisciplinary analysis, within the SimCenter 3D ecosystem, everything happens within the same platform and the ways of automating a lot of the process where there's less handoff, less handwork to do, and therefore less errors that occur as you go through the process. All right, thank you very much. So if you have any questions, I'm here for the next few minutes to answer.
Great, thank you very much. Just checking online to see if there's a question. Yes, I see one. Does HEEDS only work with Siemens products? Will it work with Thermal Desktop?
Yeah, HEEDS can work with other products as well, and that's one of the good features is that you can tie in data from one software to the other. It's not restricted to a particular platform.
Great, thank you.
Zoya, could you comment on the computational environment that you used? Was this on one machine, or was it a heterogeneous environment? Did you have Linux, Windows?
Oh, yeah. So all of that is possible. I ran all of this on my machine, a single Windows machine, and had no problems. I mean, but if you wanted to, you could also launch these cases on a cluster. You can launch these cases on a in parallel. So, for example, if you have, let's say, 150 evaluations to do, you don't have to do one at a time. You can do 5 at a time, 10 at a time, as long as you have the available resources to do so. So yeah, it's possible to really scale this up if you wanted to. Okay, just any further questions?
I'm not seeing any. Thank you very much for the presentation. Our next presentation